Hello, my name is Rogério, and this is my contribution to the special session on ethics. Okay, let's start from the obvious. The main purpose of feedback control systems is to remove the human from the loop. Either the humans are not able to perform a particular task or activity properly, or they are not able to perform that activity at all right? So, hence the purpose, hence the feedback control systems to provide a certain kind of services that the humans are not able to provide. On the other hand, you've got the self-adaptive software systems, in which are essentially social technical systems. And, uh, and for this type of systems, humans have to be considered right from the inception of the system. Otherwise, the system is bound to fail during deployment. So, so whether to ignore humans or to consider humans, right? This has an impact on how systems are developed, deployed, and evolved, right? So, and hence the reason of this talk, like trying to be a bit provocative. What I'm trying to raise is, as software engineers, what are the challenges that we face in order to ignore completely humans? Okay, so, but before I'm going to the actual talk or the actual topics, let me talk about fridge thermostats. So the basic role of thermostats is to regulate the temperature inside fridges, right? So whatever the fridge is full, whatever the fridge is full, it's empty, whether the door is continuous open and close, whatever the situation of the fridge, the purpose of the thermostat is to regulate and maintain that temperature. Now, I wonder, based on this, I wonder how many times have you checked the temperature of the fridge? How many times you went with a thermometer and checked whether the actual temperature of the thermometer was the same as specified in the fridge manuals? A step forward, right? So let's assume that you became suspicious of the thermostat. The thermostat perhaps might be malfunctioning. So you take the role of the thermostat. So what you're going to do now is every 5 minutes, 10 minutes, half an hour, 1 hour, you go to the fridge, measure the temperature, and start adjusting the dial in order to increase or decrease the temperature. Now, if you think that the activity of controlling the temperature of a fridge is simple, you are truly mistaken, right? Although it's a single physical variable, it's quite difficult to control the temperature if the human is not aware of the dynamics of that variable. And this can be confirmed by the experiments that Dorna has done on supermarket fridges involving humans. So they asked humans to control the temperature of the supermarket fridge, and of course, the results were, as expected, a completely disaster. Now, let's go back. Let's go to the main theme of the talk, which is the point of no return. The point of no return in terms of aeronautical terms is a point on a flight at which a plane is no longer capable to returning to the point of departure. And this is represented in several contexts, the context of parachuting from an aeroplane. So once you jump, all right, you don't expect to be able to go back to the aeroplane. Once you jumped, it's you, your parachute, and luck. The same thing happens with rockets. When you launch a rocket, right, you don't expect the rocket to land back on the platform. If the rocket lands on the platform, it's not anymore a landing, it's a disaster, it's an accident, right? And in terms of more accessible systems, you've got in this two-hand industrial presses or two-button industrial presses, in which trying to increase the safety of manipulating this equipment, press equipment, trying to control the when to stop, for example, when to stop the press in order to avoid an operator to have the fingers of the hand crushed. So, what I did next is was trying to find out what point of no return means in the context of self-adapted software systems. And the point of no return in self-adapted software systems is that in their technical maturity, when any human involvement with its operation is perceived to create more harm than benefit. So there is evidence, you collect evidence regarding the involvement of humans, you capture evidence regarding the risk involving the ignoring humans or removing humans from the loop. You compare that evidence in terms of risk, and you see when is the point where there is no more justification to involve the humans. When there is no more justification to involve the humans, all right, you just completely remove the humans from the loop. So whatever the humans can do might do more harm than benefit in the operation of the system. So I'm not talking so much in terms of operation here, but I'm talking about maturity in a particular technology, or the maturity in collecting evidence in order to show that humans are essentially become useless in a particular system. Okay, so I'm going to talk. The main theme essentially is about configuration. So in complex systems, one important aspect is the configuration of that system, and more importantly, is the awareness of the awareness that a human might have of the configuration of the system. And a good example of this is the study that performed by John Rushby about 25 years ago, when he's trying to understand what's the interaction between pilots and cockpits. So for him, mental models are a fundamental guide for pilots to interact with automated systems. So the mental model essentially are sourced by instruments, right, as a result of a rigorous training supported by manuals. Essentially, a layperson arriving to a cockpit, all the dials, switches, and lights and screens are completely meaningless, don't provide any useful information. But training starts associating value to those switches, screens or lights, whatever, right? And that's the training is not sufficient, because there are some circumstances in which the pilot has to look for the manuals, to look for exceptions and very exceptional circumstances, operational circumstances in which are very rare in training, so they've got to go for the manuals. So this is the mental model of pilots, let's say. Now, so you've got the instruments feeding the mental model of the pilots, but the information from that instrument essentially comes from sensors, all right? So sensors provide a perspective of reality. So there is the real world, is the real world is captured by the sensors. The information is presented in the instrumentation. The pilot observes or simulates that information based on the training that has received. Now, it's very beautiful, but you see, there is a lot of transformations here, which can be source of discrepancies. So one of those discrepancies is between reality and instrumentation. Sensors might malfunction, sensors might become inaccurate, sensors might fail, essentially. And what's happening is that whatever information is provided in the instrumentation is not an accurate representation of reality. So the second source of discrepancy is essentially between the instrumentation and the mental models. If it might be the case that the pilot receives the wrong training, and what's happening in the instrumentation is not able to simulate as accurate representation of reality, right? So, and it might be the issues that might influence this perception of the pilot of the instrumentation, which affects the mental model of the pilot, right? And of course, those discrepancies can lead to hazard situations. Now, Putting this in the context, giving examples of this, I've got two aeronautical accidents. One is related to the Air France flight 447, a flight from Rio to Paris, which essentially plunged into the mid-Atlantic Ocean. Right, this was Airbus, and the initiating event in this accident was essentially a failure of the sensors. Right, so what's happened there? The sensors have failed, or the instrumentation the instrument started presenting information which wasn't inconsistent, was confusing instrument. The pilots essentially lost awareness of the aeroplane, and what the pilot actually was doing, the actions, was not representative of the information shown in the instruments, and of course, right, the pilot took the blame. And that's essentially one of the reasons for this accident is known as the automation paradox. It's these type of systems are so much automated that the mental models of the pilot not stimulated, continue stimulated. So, and what's happened is that the mental models, right, start drifting, let's say, from the reality, right? Now, another example is a more recent example is the Boeing 737 MAX accidents. Again, the cause was a failure in the sensors. But associated with this failure, also there was a component in the system, the MCAS, which had now reckoned there was some bugs, some problems in that component, right? So nevertheless, right, what differentiates the Boeing accident from the Airbus accident is the fact that this component, right, which was part of the configuration of the aircraft, wasn't known to the pilots. So this component augmented the usual flight of the maneuvering, augmented the maneuvering of aircraft, but the pilots are not aware of it. We're not aware of its existence. We didn't have received any training, and so it was impossible for the pilots actually to have an accurate representation of, or the accurate mental model of the operation of the system, because essentially what how the system was behaving was nothing related to their own experience, right? And of course, for the Boeing MAX, the manufacturer took the blame, and so far, 18 months after the accidents, the planes are still grounded. All right, so let's move this conversation, the configuration, to our in the context of self-adaptive soft systems. Let's talk about architectural configuration. So one way of soft engineering is to deal with the complexity of reconfiguring systems was to deal with the configuration architecture level. All right, so you might have a self-adaptive system as a component of autonomous system, and this component is able to adapt its architectural configuration through several distinct adaptations. So starting from initial configuration, you can go through several configurations, architectural configurations, depending on the changes affecting the system. So, and this can go smoothly without even affecting very much the expected behavior of autonomous systems. So everything is well until the system reaches a boundary condition of failure. A boundary condition of failure is when the system recognizes that or is not able to provide the services as specified. So when this happens, all right, usually there is a human there. So is the role of the human now to establish a trajectory of the operational state of the system. Right, so is the role of the human knowing from to establish this trajectory from a known configuration to the alarm or exceptional configuration, and trying to figure out what's supposed to be the actions that should be taken in order to bring back the system from crossing that boundary condition of failure. So, as you can see, this trajectory might become extremely obscure, or actually the operational states of the system in exceptional situation, alarm situation, might become very obscure. So the pilot is not able to take informative action, essentially. So essentially based on luck. So, so you've got this situation. Now the alternative actually is to remove the human. So you should have, or you should build, you should develop systems which are essentially humanless, right? And that's the line that I'm just trying to raise in this talk. Now, because reality, all right, the reality is that there is always a human at the end of a loop, and the guardian of the guardian of the guardian is a human, and the fallback is a human. So whenever there is this, when it is there is this unexpected conditions or changes, or so, and the system not able to deal with it, all right, we design systems in a way that humans are there in order to take care of the system. So my question now is whether you can rely on this reality, right? Whether this will be the reality in the future. So there is always a human, right? So, and if that's not the case, right? If you need to remove completely the human, right? So what needs to be done in order to achieve that? What needs to be done in order really, right from the inception of the system, there is no humans here, right? So how should I build my system considering there are no humans? Now, now going back to my initial slide, what I'm trying to say essentially, what you need to have or need to achieve in order for us human to perceive self-adaptive systems as fridge thermostats. All right. So in order to achieve that, what we need to do. Now, I've reached the end of my talk. I just want to leave in a more rigorous way the question that I would like to be answered, all right, or by the challenge essentially associated with my talk is what assurances software engineers need to provide on the resilience of self-adaptive software systems in order for these to be an integral part of autonomous system. So this is the end of my talk. Thank you for listening, and I'm waiting for questions.